Okay, question 10 shows a student after rubbing a balloon on his hair. The balloon has become charged, and we can see it's a negative charge and it is pulling the hair. And we are to describe the forces that are acting on the student. So it's an attractive force and it is an electrostatic force. So it's an electrostatic force, an electrostatic attractive force, and there's your 2 marks, one for electrostatic and one for attraction. Now, part B is a calculation to calculate the charge transferred by the spark. So an earth conductor was brought near the charged student. A spark jumped between the conductor and the student. The potential difference between the conductor and the student was 2.5 kilovolts, and the energy transferred was 0.005 joules. So calculate the energy transferred. So calculate the charge transferred by the spark. So voltage equals the energy over charge. The reason why I've used that is because we are looking for the charge. We have been given the energy and the voltage here. So what connects voltage, energy, and charge is voltage is equal to the energy transfer divided by the charge. And the charge, rearrange this formula, charge equals the energy divided by the voltage. The energy is 0.005 joules. The voltage is given in kilovolts, so we need to convert that into volts, which is times by 1,000, which is 2,500 volts. So 0.005 divided by 2,500 gives us 2 times 10 to the minus 6. And that is coulombs. So the charge is 2 times 10 to the minus 6 coulombs. Part C, a defibrillator can transfer a charge to regulate a person's heartbeat. So figure 2 shows a defibrillator, and what we are doing in this question is when a defibrillator is in use, the potential difference of 4,800 volts is applied across a person's chest. A charge of 0.16 coulombs passes through the person's chest in 4 milliseconds. Calculate the resistance of the person's chest. So I go straight to the formula. Resistance is equal to voltage over current. Have we got the potential difference to voltage? Yes. Have we got the current? No. Okay, we've got charge and time. Can we find the current using charge and time? Yes, using the formula. Current is equal to charge divided by time. Okay, so current is equal to charge divided by time. The charge is 0.16 coulombs. The time is 4 milliseconds, but that's not seconds. So we've got to convert into the standard unit of seconds. So we divide by 1,000 to get it into seconds, which is 0.004 seconds. And that is 0.16 divided by 0.004, and that gives us 40 amps of current is passing through the person. Now we've got the current. We can use this formula here. Resistance is voltage over current. The voltage is 4,800 volts. The current is 40 amps, as I've just calculated. So 4,800 divided by 40 gives us 120 ohms, and that's your resistance, 120 ohms. So how are the marks distributed? There's 1 mark for converting into milliseconds into seconds, putting into formula, rearranging formula and calculating 40 amps. So there's a couple of marks there, and then you've got a couple of marks here. 4,800 divided by 40, and then you've got a couple of marks here, last mark for 120 ohms. Question 11. A student measured the width of a solid metal cube using a digital micrometer. The figure below shows the micrometer. So here is a micrometer. You may have not seen this piece of equipment before, but it measures the length and the width of a cube. So there's a cube in between, and it's reading 18.45 millimeters. So that's the width of a cube. Now here it starts off by saying that the resolution of the micrometer is 0.01 millimeters. That means that the smallest measurement that a micrometer can make is 0.01 millimeters. It says the student could have used a meter rule to measure the width of the cube instead of a micrometer. So explain how using a meter rule would have affected the accuracy. So we are looking at accuracy of the student's measurement of width. So we know that a ruler, if you when we look at it, the smallest measurement that we can make is a millimeter. So the resolution of a ruler is a millimeter, whereas a micrometer can actually measure to 2 decimal places. So it's more precise. So therefore, a micrometer has a higher resolution, more precise measurements. And in actual fact, it's 2 decimal place in terms of millimeters. So this means that there is more uncertainty in the ruler measurement. So when we take the ruler measurement for the width of a metal cube, we're going to measure to the nearest millimeter. And so the value of the width is going to be slightly more uncertain. This means that the ruler measurement is less accurate. So one for measuring less accurate for ruler measurement, and two for comparing the resolution of a ruler with the resolution of a micrometer. And those are your marks. Part B. The mass of a metal cube was measured using a measuring balance, or in other words, top hand balance. The balance had zero error. There are two ways to reduce zero error. And one is we can remove the metal cube from the top hand balance, zero the balance, and then place the metal cube back on the balance, and it would measure the correct reading for the mass. However, another technique is record the mass when the mass is removed. Okay, so remove the cube, see what the measuring balance is reading, and then knock that value off to the value of all future measurements. So put the cube back on the mass balance, whatever it says, take the value of no mass on the measuring balance off it, and it will get the mass of the cube. So those are your two techniques. Part C, the final question. You've got the cube of width 18.45 millimeters, the density given of 8 times 10 to the 3 kilograms per meter cube, and you're working out the mass. Okay, so to find the mass, we look at the formula that links mass, the width of the cube, and density. So we have a formula that is density is equal to the mass divided by the volume. We want to work out the mass, so we rearrange this formula. Mass is equal to density multiplied by volume. Density we've got given, and it's in the right unit. Volume we haven't, but we've got the width of the cube. It's 18.45, and it's millimeters, and that's the wrong unit. We need meters. So how do we convert millimeters into meters? We divide by 1,000. So 18.45 millimeters divided by 1,000 gives us 0.01845 meters. So we've got the width of a cube as that many meters. So how do we find the volume? We'll do that multiplied by itself 3 times. So it's 0.01845 cubed, and that is the volume of the cube in meters cubed. So 6.28 times 10 to the minus 6 meters cubed. So now we've got the volume. We multiply that density of 8 times 10 to the 3 with the volume that we've just calculated, and we get that the mass is 0.05 kilograms. That's 50 grams. That kind of makes sense. This is around about 2 centimeters in width. So it's a cube that is approximately 2 by 2 by 2. So it's quite small in size. So therefore, you're going to have a small mass. So this 50 grams sounds about right. Okay, so if you're looking at a mass that's in the 50 kilograms, 2 centimeter by 2 centimeter by 2 centimeter. Those masses don't make any sense. This is more reasonable. Okay, so how are the marks distributed? Converting into meters, there's a mark there. Finding the volume, there's a mark there. Putting the values in, rearranging the equation, there's a couple of marks there. And then your final answer of 0.05 kilograms, and there's your final mark.